For section 11.6, we're going to talk about polar equations for conics. And before we dive into that, we have two topics that are really just review. I was going to originally do it as one topic, but it was getting kind of long, so I decided to split it into two topics. So for topic one, we're going to review eccentricity and polar coordinates, okay? So you need to remember that eccentricity, just generally speaking, tells us how much a shape deviates from a circle. So when we're talking about these conic sections, circles, ellipses, or I guess it's ellipses, I don't know, the ellipse, the hyperbola, the parabola, eccentricity is a numerical value that tells us how much this deviates, this shape deviates from a circle, okay? So that is kind of the general definition, okay? Now, I also have that for any point on a conic section, we're going to look at this in terms of like ratios. So for any point on a conic section, the ratio between the distance from the focus and the distance to the directrix is called the eccentricity. Okay, so we're going to look at this kind of in two different ways. Okay, now when we were talking about the eccentricity very specifically for a hyperbola and an ellipse, we could use this formula right here to calculate the eccentricity. And we did this just a little bit in the previous sections where we talked about the ellipse and we talked about the hyperbola. Okay, so what this little guy right here is saying, let me write it over here. We have E equals this over this. What this is saying is this little d and then in parentheses, big P comma F. This is just saying we're looking at the distance from a point to the focus, either focus point, okay? And then we're looking at the distance from that same point, whatever point we're interested in, to the directrix. We will also, at some point, see this written like this. So we're again saying the distance from some point to the focus compared to some point to the directrix, okay? So don't get too bogged down in the notation here. It's really nothing crazy. We're just comparing two distances. Now, if you're dealing with a circle deviates from itself exactly none, okay? So if you ever get that eccentricity equals 0, then that means you're dealing with a circle. Now, if you have an ellipse, we find that the eccentricity is always going to be some number between 0 and 1. So it's going to be less than 1, greater than 0. So some non-negative number, less than 1. For a parabola, we're going to get that the eccentricity is exactly 1. And then for a hyperbola, the eccentricity is going to be a value greater than 1. And in a little bit, I'll show you, it's going to be the next topic actually. I can kind of explain more why that is so. Okay, now we have some interesting stuff here, and I'm going to revisit three of these statements down here in the next topic. We have if E is 1, the conic is a parabola. We already have that in this table. But what's really important is the axis of symmetry is going to be perpendicular to your directrix. So remember, when you have a parabola, okay, you have some axis of symmetry which goes through the center of the parabola. It goes through the vertex. So with a parabola like what we have here, where it's opening up, or this could be the same way if it's opening down, your directrix would be here. So the axis of symmetry is going to run perpendicular to the directrix. Now, if we had a parabola that opened left or right, the axis of symmetry is like this. Well, again, the directrix is going to run perpendicular to the axis of symmetry. So this statement right here that's highlighted, very important. Now, if E is less than 1, the conic is an ellipse, okay? And what we have here is the major axis is perpendicular to the directrix, okay? So if we have an ellipse like this, we have the major axis that runs like that. Well, then the directrix ends up being, let me draw the directrix as kind of like a solid line to make it a little bit easier to understand. And when you're dealing with an ellipse, it actually has two directrix lines. They kind of go like such. So notice the major axis runs perpendicular to the directrix. Same thing if we had a parabola, an ellipse that did something like this, we would have our major axis running down the middle of that ellipse. And then the directrix would be some line like this. Okay, so when you're dealing with an ellipse, the major axis, the one that contains the vertices, the one that contains the foci, it's going to run perpendicular to the directrix. And then finally, if E is greater than 1, we know that we're dealing with a hyperbola. But even more important, the transverse axis is perpendicular to the directrix. So remember, a hyperbola can go kind of like this. That's a terrible curve right here. Okay, well, you'd have your vertices, your foci, your center, your transverse axis goes through those, and it's going to run perpendicular to your directrix. So you have a directrix here, and then again, with a hyperbola, you end up having two of these directrix lines. So again, the transverse axis is going to be perpendicular to the directrix. And then similarly, you can have a hyperbola that does something kind of like this. Well, we've got our transverse axis that runs here. It contains the vertices, the foci, the center, and then the directrix lines are going to go kind of like such. Okay, so we need to understand what our directrix is perpendicular to. With a parabola, the directrix is perpendicular to the axis of symmetry. With an ellipse, the directrix is going to run perpendicular to the major axis, and for a hyperbola, the directrix is going to run perpendicular to the transverse axis. So those three statements are really important, and I'll bring them back in a bit. Now, polar coordinates, we talked about this a whole bunch in chapter 10. So we talked about like what is a polar coordinate, how to convert between rectangular and polar coordinates, how to take polar equations, convert those to rectangular equations and vice versa. Okay, so what you need to remember is the pole kind of acts like the origin. So when you're in the polar coordinate world, we call the pole kind of like it, again, like I said, it acts like the origin. And then we have the polar axis kind of relates to the positive x-axis. So we have that labeled here, okay? So you can see the pole corresponds to the origin and the polar axis corresponds to that positive x-axis. And as we were converting between polar coordinates and rectangular coordinates, we found there were these really, really important relationships that we had to know. First and foremost, go ahead and fill this in. A polar coordinate is of the form r theta, where theta is an angle and r is a distance from the pole. Okay. Now, the relationships that we had to understand was, well, they're all listed here, but we had to understand that r squared equals x squared plus y squared. That was really, really important for us when we were converting between the two forms. We also know that x equals r times cosine theta, y equals r times sine theta, and tangent of theta equals y divided by x. And then these two kind of go together. We also know that if we have tangent of theta equals y over x, if we have y over x, in order to get theta, we would have to take the inverse tangent of both sides. So we can then say theta equals inverse tangent of y over x. So all of those were really important, and you will see at least two of these later in this worksheet. So that is kind of a review of eccentricity, kind of a review of these different conic sections. And what's really, really important that you must understand about these is what is perpendicular to the directrix. Okay, we're going to talk more about the directrix again. Again, I was going to have it as just one topic, but it was getting kind of long, so I decided to split it into two. And then just don't forget your polar coordinates stuff. Okay, so when we come back, we're going to talk more about the directrix and eccentricity, and you're going to kind of see why the stuff in this table is true. And then we'll finally get to the actual polar equations for conics.